An object can have many forces on it and yet sit perfectly still. A book on a table, a bridge holding its load, your own body right now. Stillness does not mean no forces, it means the forces are balanced. This unit is about forces in balance and the new ideas needed to handle them, turning effects and pressure. This unit builds in 4 moves: drawing the forces on an object as a free body diagram, the turning effect of a force through moments and couples, the idea of density and pressure, including why things float. Let's start by getting every force onto the page. The first skill is drawing a free body diagram. Isolate one object and draw every force acting on it as an arrow, and nothing else. Weight pulls down from the center of mass. A surface pushes back with a normal contact force. Tension pulls along strings and friction opposes sliding. Miss a force and the whole analysis collapses. For an object in equilibrium, 2 conditions must hold. First, the forces must balance. The resultant force is 0, so up equals down and left equals right. A neat trick is that 3 forces in equilibrium always form a closed triangle when drawn tip to tail. If they don't close, the object is not in equilibrium. A force can also turn an object, and that turning effect is the moment. The moment of a force equals the force times the perpendicular distance from the pivot. That word perpendicular is where marks are lost. It is the distance at right angles to the line of the force, not along it. Push further from the hinge, or push harder, and the turning effect grows. When something balances, the principle of moments applies. Total clockwise moments equal total anticlockwise moments about any pivot. A couple is special. 2 equal and opposite forces that don't share a line, producing pure rotation with no resultant force. Its turning effect, the torque, is 1 force times the distance between them. Density is simply how much mass is packed into a given volume, mass divided by volume, measured in kilograms per cubic meter. It is a property of the material, not the amount. A tiny ball bearing and a huge steel girder have the very same density, because density does not care how big the lump is, only what it is made of. Density is what decides, in the end, whether something floats. It is also the bridge to pressure in fluids, because a tall column of dense liquid weighs a lot, and that weight presses down on everything beneath it. So before we can understand floating, we need to understand pressure. Pressure is force spread over an area, force divided by area in pascals. The same force on a small area gives huge pressure, which is why a sharp knife cuts and a drawing pin pierces. In a fluid, pressure grows with depth because the deeper you go, the more liquid sits above you. That pressure is density times g times the depth. Because pressure rises with depth, the bottom of a submerged object feels more pressure than the top, and that difference pushes it upward. We call this upthrust, and it equals the weight of the fluid the object displaces, the principle of Archimedes. If the upthrust matches the object's weight, it floats. If not, it sinks. Floating, finally explained. Here is the whole unit as one poster. Draw every force on a free body diagram. For equilibrium, 2 things must be true. The resultant force is 0, and the resultant moment is 0. A moment is force times perpendicular distance, and a couple is 2 equal opposite forces giving pure rotation. Density is mass over volume, a property of the material. Pressure is force over area, and in a fluid it grows with depth as rho gh. Upthrust is the weight of fluid displaced, and when it equals the object's weight, the object floats. And the boundary fence so you do not over-revise. Work, energy and power are their own unit, the stretching and deformation of solids comes next, and the deep gas laws and thermodynamics wait for a 2. Here it is forces in balance, turning effects, density, and pressure.